to our technical webinar today. It's great to have you. Thank you for taking your time out of your day to join us today. I'm just going to take you through some housekeeping, and then we'll go into the real reason why you're here. Pratik, could you just move on to the next slide for me?
Yes, sure.
Thank you. All right. So as you'll notice, your sound and cameras are off. We do that just so there's no disturbance in the webinar itself. But if you have any questions or whatsoever, please pop them in the chat. There's also a Q&A function, but I'll double check the chat so we don't miss anything. All right, next slide. Yeah, so we're recording this session in about 2 days' time. You'll receive an email from us with the slides and the copy of the recording, so you can watch it back at any time. There is also a certificate of attendance for this session. You will only receive your certificate of attendance if you fill out the form that we will show you at the end of the slide, okay? So if you're not able to do it now, just make sure you scan the QR code or you copy paste the form, which I can put in the chat at the end as well. And you can do it in your own time, but just do it within 2 days of today. Otherwise, you won't receive your certificate of attendance. All right, next slide. Okay, so just a little bit about ECT. So we are a higher education institution based in the UK. We have let me just admit some people here. We have
I'm doing
electrical
that. I'm doing
engineering.
that. You can go ahead, Lucy.
Oh, you are. Oh, look at that. Amazing. We're a team. We've got industrial automation and electrical engineering programs, both across bachelor's and master's. We offer them in full-time and part-time. So if you want to upskill while you work, we have a couple of really great options for you. Next slide. Please please stay lawful and respectful in the comments. I will be monitoring the chat as we go, but I'm sure we won't have any issues there. Next slide. All right, handing over to you. Thank you, everyone.
Thank you, Lucy. Thank you so much for inviting me to deliver this lecture. I'm highly thankful to ECT for giving this opportunity to talk to such a learned group of individuals present in the session. And I would like to start with my introduction, but before doing that, as you know, today's expert lecture is on computer-aided design and manufacturing. And I'm sure that Lucy just said you that they are having some upskilling programs, right? So by the end of the lecture, you will be surely understanding what importance does the topic have in upskilling your skills today. And at the end of the session, though, Lucy will be telling you about the various courses that are designed, which will fulfill your aspirations to go into and venture into the field of computer-aided design and manufacturing. So with that, I come to brief introduction of myself. I am Dr. Pratik Shah, and that is how I look like. Right. I am an associate professor working in India in a reputed university. I hold my PhD doctorate in mechanical engineering and have got over 26 years of experience in academia. I have been working since the last 8 years in the field of research and actively researching on the fields like computer-aided design, computer-aided manufacturing, computer-aided engineering, manufacturing processes, automating manufacturing processes, implementing industry applications pertaining to advanced manufacturing process and a solid state welding process in specific. Right. I have published more than 30 research papers in the reputed journals, international as well as national journals. You can go through my Google profile and you will find lot many publications over there. I have also been granted two patents for the product inventions. Both of them were a product invented. I also guide many PhD scholars. At present, I am guiding four PhD scholars, and they work in the field of manufacturing, design, automation. They also work on implementing certain internet IoT tools in industries. Right. I am also a reviewer of reputed journals. And so that is my brief introduction. And with that brief introduction, I would just like to on to the next slide. And I would just switch off my camera so that Lucy, it won't be an issue, right? Or do I need to keep my camera on? Because there might be some bandwidth issues with the audience.
Um, I can hear and see you just fine. Are you having some issues?
No, no, I don't have any issues. I
Okay.
don't have any issues. Okay, so I will keep the camera on.
Okay. All right.
Okay, fine. So that sets up the agenda for today's our expert lecture, right? We'll be talking something about the introduction and implementation of CAM vis-a-vis Industry 4.0. I'll be talking something about computer-aided designing and geometric modeling in details, followed by computer-aided engineering. I'll also talk something about Lucy, can you help me in maximizing my screen? Because at present I am seeing the slides are I'm extremely
Let me see. If you press at the top, do you see take control?
take control.
At the top of the webinar.
Uh, the-
It looks it's full screen for us. Is it not full screen for you?
no, 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 it's not
Oh,
full.
do you
Uh,
do you want to stop sharing and share again and see if that works for you?
just a minute, just a minute. I'll just figure it out. Just give me a second.
No worries.
Okay, okay, I have done that. So I'll be also taking one case study where I will be showcasing the implementation of computer-aided design, computer-aided manufacturing in the overall product development, followed by the future trends which the topic includes. And last but not the least, I'll be referring to some author, some text where I have been using this for making my presentation. Okay, so before we start with the topic, I would just like to stress upon the industrial revolutions that took place during recent centuries, right? As we know, the industrial revolution, I'm talking about this slide because it has got certain context with pertaining to Industry 4.0. That is what we are going to discuss today. But we know that Industry 1 took place way back in 18th century when steam engine was discovered, right? Steam engine was discovered by James Watt. And at that time, normally people change over from cottage industries. Cottage industry means they were manufacturing certain things at home with some hand tools, something like that. And they shift over from cottage industries to some mechanical productions, right? Then in 19th century, there was development of electricity. Though we normally do not give credit of development of electricity to one scientist, to name a few of them, we do have Benjamin Franklin, Thomas Alva Edison, who invented and who did much of the work in electricity, wherein mass production came into existence. And we set up with assembly lines. By the 20th century, we started using electronics and ICT. That is where we came around with tools like CNC machines, that is computer numerical controlled machines, numeric control machines, direct numerical controlled machines. We came about with development of automats, which are normally used for mass production, right? So that was industry revolution, industry 3.0. And what we are witnessing at present is industry 4.0. We will be swiftly switching over to industry 5.0 also. I'll just take some time to explain what industry 5.0 is. But we say that industry 4.0 is basically done with highly automated tools like the use of robots, 3D printing, Internet of Things, artificial intelligence, big data analytics, cloud computing. We talk all about this. We'll just have a look at industry, the industry 4.0 will. But, and then we'll start with our today's lecture on computer aided design and manufacturing pertaining to industry 4.0. By the way, uh, Industry 5.0, Industry 5.0 basically is the evolution of next industrial production line where we normally aim to create manufacturing systems which are human centric, right? When we say human centric, at present it has industry 4.0 has an image that it will abolish jobs of many people, but when we talk about industry 5.0, it is human centric where we have coordination between the machines and human beings, and it's also sustainable and more resilient. Now, this is one thing which we need to take care about because in Industry 4.0, we normally talk about big data analytics, cloud computing, everything we do have on the cloud. And so there are also chances of cyber attacks and data breach. So that is one of the major concerns for the industries which are implementing these solutions today. So Industry 5.0 basically is adoption of industry 4.0 wherein it is more human centric, wherein it is more sustainable and more resilient. Now when I say it's more sustainable, we normally say that it will the systems are meant to reduce the use of energy or wastage of energy, and it will give some sustainable solutions pertaining to environment or environment friendliness, right? So with that, I come to the building broad. I normally call this as building blocks of Industry 4.0. The Industry 4.0, as discussed in the previous slide, it consists of Internet of Things, IIoT, or you can say Industry Internet of Things. Again, it has got a subset which consists of AI and ML, artificial intelligence and machine learning. Though we are not supposed to go into the details of each and every building block of Industry 4.0, but we know the role of AI and ML, right? We now say that machines or the machines which normally run through years are now bound to learn something. There are machine language coding which are done, which trains the machine to learn from the mistake that it does. It trains the machine with the help of AI codes, and also it helps in performing the task in a better way, right? We do have robotics as one of the component. Data analytics, we say that today it is era of data where data plays an important role, right? Because all of these are connected. When you have got huge amount of data, then only you can go and build AI ML models, right? Cloud computing, AR, VR, that is augmented reality and virtual reality. I'll talk about this something in my lecture also. We also have got blockchain, additive manufacturing, and system integrity. Right. So these are basically the common building blocks of Industry 4.0, and we'll just try to know where our today's subject topic CAD, CAM, and CAE falls into its domain. Right. So to start with, computer aided design, as you all are aware, is use of computer in assisting and creating or modifying designs. Now, when we say design, design is something that is basically expected for the product which is not into existence, right? If it is into existence and we do some modeling or we do some 2D sketching, it is basically known as designing. It's basically known as drafting and not designing, right? Whereas once we design something, the use of computers to prepare or to machine the product, or which facilitates in machining or actually realizing the product, is computer aided manufacturing and computer aided engineering. Though I have listed it over at the third point, but normally computer aided engineering is carried out after computer aided design, and then CAE is followed by CAM, right? Where CAE is use of computer softwares for engineering analysis and simulation. So when we design something, the product is new in the market, it's not yet tested. So after designing, we directly do not put a product into manufacturing, right? Say, let us take an example of automobile or a cell phone for that case. Normally, when cell phones are designed, we now and then we every 6 months we see companies coming out with new cell phone models, right? So they are bound to do so because they need to remain competitive in the market, right? So normally what they do, they come out with a newer model. The model is first designed into the computer, and say for like example, like mobile phones, they undergo test like drop test. So whenever a mobile falls, the designer tries to maintain its CG in such a way that it falls on the corners and so the screen is protected. So they undergo normally drop test. So that type of testing is basically in the phase of computer aided engineering, where now people have started using softwares in order to analyze the product, right? So with that note, I'd like to start with the first topic, computer-aided design. And before we move to the computer-aided design, I'll just talk in brief about what a design is. And in order to explain what a design process is all about, there are various models available in standard literature, in open literature, which talks about the basic concept of designing, right? But I like this model developed by Shigley, which basically talks about the design steps, the major steps which are involved in design. And I put up this slide for a very specific purpose, that when we learn about CAD, we should also know what a design is about. Then only we can put it in terms of computers, or then only computers could assist us. Right. So the design basically starts with recognition of need. We normally don't go for designing a product until and unless there is a need to design it. I repeat my statement again. We normally do not design anything or a product till there is a need to design, right? Because design involves high amount of R&D costs, and it is a costly affair many times. We are just talking about automobile. I mean, we are talking about cell phones, but let us talk about an automobile company. Automobile companies also come out with developed models every 2 or 3 years, right? So they are not changing the models now and then like cell phone companies, but after 2 or 3 years, when the test in the market starts to fade. People think about something else or something new features in the model of that particular company. They come out with a newer model. Now, think about a automobile company which comes with a newer version. The entire press tools to design the body, the door panels, the dashboard, all of them would change, which involves high amount of R&D cost, right? So recognition of need, I won't be going into much detail. It asks for customer survey, it asks for feedback, etc. The phase itself is a longer phase, but where should be this phase? After that, the problem is defined because designing is not only one engineer's cup of tea. There would be a team of designers which would be working on a product. So the definition makes everybody clear what is to be done. Next comes the synthesis phase in which the conventional design, I'm talking about conventional design where we were not using computers right before 2000 or 1990s. There was no evolution of softwares. And so people used to use the drafter, the pencil and the drawing table in order to create some basic designs. After that, once the design was created, in the synthesis phase, they also decide upon the material which the product is made up of, etc., etc. They go for analysis and optimization, where conventional design people used to create a prototype. That prototype was made up of either clay or wood or any material which was easily formable and which was easy to form, right? And they used to reduce the actual loading conditions to fit to that material and tried to analyze, which was though not an optimized way of doing. After that, the design or the analysis or the product was evaluated, followed by presentation. Now, if evaluation failed, again, people used to go to redesign it, change the material, change the section thickness, change the dimensions, give more material or use newer materials with higher strength. Again, the same process starts. And once the evaluation clears off, people used to take into final production line. But with evaluation of computer aided design, people now have changed the entire role of computer or role of design pertaining to computer aided designing. So people normally say that when we create a model, it's basically a digital prototype. It's basically a digital prototype. The first two phase though remains the same, that is the recognition of the need and problem definition. But the synthesis phase has now taken up by geometric modeling. We are having many softwares into market which directly which directly creates which directly creates 3D model, which directly creates 3D model. So synthesis phase where people used to use conventional drafters, drawing board, pencils, etc. They now use CAD softwares. CAD softwares in order to create the solid models of the product. That would give a better visualization, better understanding of the product, what is being created. The analysis phase has taken up a shape of engineering analysis, wherein 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 again different set of softwares are used to undergo solid physics analysis, thermal analysis, vibrational analysis, structural analysis. You name the analysis and you have got tools in the market which can do that analysis. We will be talking in details of that also, right? Again, evaluation, we normally say that designing and evaluating is again done with the help of computers. And last, there is automated drafting. So once the design is approved, it undergoes the analysis. It is now cleared with the analysis. We will be having facility to create the drawings automatically with the help of the software if we are having 3D models available. So you can imagine a world where you need to imagine something, the idea is in your mind, you need to put it on a pen and paper, and you need to explain to other engineers working with you, or you are requiring to explain it to your subordinates. Now it's very easily done with the help of this building softwares. And once the model is created, we always have got facilities in the softwares itself to create drawings, right? When I say drawings, still drawings have got their own role in production. We never release any kind of 3D models for production. In shop floor, we still require a front view, top view, and a side view. That is the orthographic view of the object. If we talk about inspection, the inspection guy will also require that soft. So we cannot eliminate the role of 2D drawings. Ultimately, after creation of the 3D models, we have to create 2D drawings for production. Okay. So this is a brief about the evaluation of CAD. It started way back in 1960s. In 1980s, we came up with a software called AutoCAD. AutoCAD is a product of Autodesk company, and it is still widely used for creation of 2D drawings in industries, right? So it is so popular nowadays that even Autodesk has made freely available this software. All the products of Autodesk are freely available to engineering institutes, to engineering colleges. They are freely available for the professors and lecturers of the institute. They are freely available for even the students, right? So AutoCAD has got its own importance. In late 90s, solid modeling software like SolidWorks, CATIA, Pro Engineer, which is now known as Creo, they came into existence and they started slowly taking up with the designing phase. By the year 2000, the softwares became more collaborative, more interactive. And at present, now what we are talking about is intelligent and connected, where CAD systems are directly integrated with machines, and the systems can integrate with directly with the machines, and with no or zero interventions of human being, it can create products. So that has now been possible with the help of tools like augmented reality and virtual reality. These are some basic reasons why we normally implement CAD, though this would be the recording would be available to you. You can just go through it. I have already briefly discussed about this. And outputs of CAD, I mean, any computer aided design can have various outputs. I'm talking about this output for a very, very noble purpose of letting you know that CAD is not only used for designing, right? It can also be used for creating various type of 3D models, that is surface models, wireframe models, and solid models. It can also be used for huge documentation where say for example, a company has got around 200 parts which are to be assembled. It can easily help in creating the bill of materials. Again, rendering and visualization, which plays a very important role in marketing the products. So we'll just talk briefly about all the three types of geometric modeling tools or geometric modeling features that normally are available with any type of CAD software. They are wireframe representations, surface representations, and solid representations. You can have a single product represented in all the three ways. You can have a wireframe of the object. Again, there can be surface models and solid models. Just will spare 2 or 3 minutes in understanding this. This you can see a nut, hexagonal headed nut, a hexagon nut, wherein the left hand side over here is a solid model, whereas the right hand side is a wireframe model. So it clearly says that a wireframe is basically grid of wires connected together. And this wireframes were basically initially meant where there were problems of storage, I mean digital storage, wherein we used to have a 4 GB of a hard disk. Nowadays, 32 GB pen drives are most common. I'm talking about the days when 4 GB of hard disk capacity was there. So people used to create models, and when they wanted to interchange or I mean, transfer it to various offices or to the clients, they used to convert that into wireframe so that it used to occupy less memory. It's basically a skeleton view, and it is, I mean, to me, it's full of ambiguity because you cannot separate out the front face and the back face. All of them are shown with the same shades of line, posing some ambiguity in interpretation, right? So it always was used when there was issues of memory or the storage, right? So basically they were visual representation of 3D objects with only lines and edges. There were no surfaces, there were no planes, no solids. They were simple and helped faster to create. And they were like skeleton where all the hidden surfaces were also seen on the same face, right? But it used to create ambiguity as several lines under different planes were also seen on the same face. Again, calculation of mass properties or calculation of volume or calculation of center of gravity, which really the modern tools give you or a solid model gives you, were not available, right? I just talked about a drop test of a mobile. In that case, the center of gravity or CG is very important, right? So you won't be able to directly calculate, directly have the center of gravity. It was normally Yeah, it is now normally done with the help of solid models. Again, you can see an assembly or assemblage of gears, which is in a wireframe. And there is also a model of a car, exploded model of a car, which is in the wireframe. These are surface model, and surface models are extensively used. Yeah, they're extensively used in automobile industries, aerospace industries. Now, surface model are the models which do not again have any kind of volume. Or say, let me just tell that they are normally used to create surfaces, or they're used to create products which are made from sheet metals, right? Which do not have thickness. So this kind of models are very much useful when you want to create some aesthetic, some good looking, some aerodynamic. We need to have aerodynamic shape on the front panel of our automobile so that the wind or when the automobile is moving on the road, it will easily cut the flow of the wind, right? We know the ancient cars which did not have that automobile, I mean aerodynamic shapes created, and the flow to the air was resisted by the body itself. So with with this, I mean surface model, it's now very easy to create aerodynamic shapes. It is very easy to create some aesthetic shapes which are used in sheet metal. Again, surface metal, if surface models, if I talk about the applications, they are widely used to design car bodies and the interiors of the car. Also, they are used in aerospace applications, right? They are used for consumer products. I mean, you talk about any casing, be microwave, a refrigerator, an air conditioner, they're all designed as surface models. And normally industrial designing where styling is focused components, where styling is of great importance. Right? It is again, by the way, defined by just the outer surface. It does not have got any volume or any planes. Whereas solid models, they give you much more clarity compared to wireframe models. You can measure the center of gravity, you can even measure the mass of the body. You can change the material. As soon as you change the material from steel to copper, the mass will automatically change, right? So it's so flexible that it will also help us in calculating the weight of the entire assembly or the component, right? These are solid models created in different softwares, and this is how normally a solid model would look like, wherein you can even you can section the solid models to see the internal parts, right? These are few advantages of CAD, where the most important advantages are, to me, are the last two, that is integration with CAM and CAE. Integration with CAM, that is computer aided manufacturing and computer aided engineering, right? And last is digital storage and sharing, right? We initially started the talk with CAD, CAM, and CAE. That is, all of them are now interconnected, and they all combinedly lead to a product design. A product design is separated into three major jargons, where we say first is computer aided design, followed by computer aided engineering, and then the manufacturing. These are common softwares, CAD softwares, which are available in the market: SolidWorks, Inventor, CATIA, PTC Creo, Siemens NX, Fusion 360. By the way, if you are a student, and many of you I know are undergoing some courses and will be more keen to take some skill-based courses with ECT, right? So if you enroll yourself as a student, you will be always free to use any Autodesk product. The last software, that is Fusion 360, is a cloud-based modeling software, right? You need not share your hard drive. You design, you create everything on the cloud, which is which is shareable to the entire people working with you on the same product, right? By the way, AutoCAD is again freely available if you are a student, and there is one more software called Autodesk Inventor, which is a modeling software, which will be also freely available to you. So the results of CAD, the output of CAD, it can be 2D drawings, it can be 3D models, it can be any data available for simulation and analysis, and any data for CAM and 3D printing, right? We are now entering into a manufacturing circumstances where we talk about additive manufacturing, 3D printing, laser based manufacturing, where 3D printing and all of them are just known as additive manufacturing, because you don't have any raw material which has to be cut, but you will be depositing layer by layers of material and building a product. Though still it is into prototype development phase. I mean, commercially, it has been adopted by few companies where we have got metal printers, but by and large, 90% this 3D printing are used for prototype development. Okay, so with this, I come to the end of the first phase, that is computer aided design. Uh, I would be happy to take some questions on this, or if you can spare your questions to the end. If you want, you can ask any questions that you feel like pertaining to. I mean pertaining to computer aided designing. Or if you want, we can do it at the end also. Whatever you feel like. So we come to the
Um,
next.
sh- sure. I
Yes,
was gonna say that maybe let's just continue, and then towards the end of the webinar, we can
sure,
take the
sure.
questions.
Okay, okay, okay. We'll do that. We will do by that.
Thank you.
Okay. Thank you. Computer-aided engineering. Now, it basically refers to the phase where you have already designed the product. You are having a digital prototype ready. Uh, Please spare your questions till end. We'll be having a Q&A session, and I will be surely replying to all of your questions, right? So, uh, we are having a digital prototype ready in the computer, and now we want to check whether that computer is going to sustain the defined or the specified loads, right? Say for example, if you talk about a shaft, when we put a shaft into practice, we know that it is going to be loaded by a torsional load. If we talk about a bearing, the inner race is subjected to various loads, right? So if we are supposed to check whether our design component will work under the specific loading condition in practice, we go for this computer aided analysis or computer aided engineering. And computer aided engineering is basically a broader use of computer softwares like finite element methods, computational fluid dynamics, or multi-body dynamics in form of a approach which is known as finite element analysis, or it is also known as FEA or finite element method, FEM, right? I'll be talking in a few slides about FE or FEM because this basically will just give a thought about the entire FEA process because it is now widely used in industry to carry out analysis. As we know, there are basically two methods of doing an engineering analysis. One of them is analytical method. Second is the numerical method. Analytical method is basically the method that we use by set rules, set principles, set algorithms where which we use standard equation. Let's say, for example, uniaxially loaded shaft by load F and the cross sectional area is A. If I am supposed to find out stress in it, I normally use an equation sigma equals to F by A, right? Sigma equals to F by A. That is, if I'm using some standard equations to solve the problem or an engineering problem, it's analytical approach. Whereas numerical approaches are basically by the use of finite element method. And FEA or FEM is a numerical approach. Now, what is a FEA or FEM? Finite element analysis is the process of predicting the object's behavior based on calculations made with the finite element method, right? While FEM is a mathematical technique, FEA is the interpretation of the results of FEM. The method, the backend thing that works with any FEA software is FEM, and the output that you are seeing is basically the analysis or the output. Just a minute. Okay, right. So where do we apply FEM? They are widely used in any engineering problem. To me, there are no engineering problems where FEA cannot be used. They are widely used for both structural and non-structural problem. You can use them for static and dynamic analysis, for buckling problem, for stress analysis in case of like bridges, buildings, aircrafts, etc. You can use it for non-structural like heat transfer, that is thermal analysis, fluid flow analysis, right? If we are supposed to, I mean, visualize the flow over airfoil, or let me talk about it in a simpler way, that if we are used to find out a volume filled liquid with a cavity, and we want to have some lid over a cavity wherein there is some flow of fluid in a cavity, and if I want to simulate that, I can do that. It is again used for again manufacturing analysis, biomedical analysis. I have not listed many of the applications over here like vibrational. It is even used for acoustics analysis, electromagnetic analysis. Various softwares are there for this specific or specified tasks. FEA process basically takes place in three steps. The first is known as the pre-processing phase, second is the processing phase, and third is the post-processing phase. The processing phase is where you need to define a geometry, right? So I told that first is CAD. You need to have a model ready in the computer, and that model can be transferred to a software which does the analysis, right? So we will be having a model which will be then taken into a CAE software. Processing step, we need to apply typical boundary conditions, and then you need to see how these conditions can be applied. So you need to control the physics. You need to identify the physics working on the part of the component. And post processing is once the software does the analysis for you, it is up to the engineer or it is up to the CAE engineer to interpret the results. These are the basic steps. The first step is right or the left over here. You need to create a model, right? A solid model. Then the next step is you need to divide the entire model into small pieces, which is known as, and that is why it is known as finite element. The small pieces in which it is discretized are known as elements. And then we need to run the analysis after specifying the boundary conditions to get some output in colored contours like this. This is a case study. This is a case study of a crank used in a bicycle to connect the axle of the bicycle to the pedal, right? So if we are interested in simulating the analysis of this particular bracket, then we need to create a model of that bracket. After creation of the model, we need to divide it into number of pieces, right? I am not going into the much details of FEM because FEM all the way is an entirely different topic, which would rather take 2 more hours. But for the basic understanding of the viewers, I'll say that there are various standard shapes available, and the model is divided into pieces using these shapes. And then the proper boundary conditions are applied, right kind of loads are applied, and the analysis is carried out, which will ultimately give you something like this, that is this color band then needs to be interpreted, right? The software is not going to do that for you, right? The software is not going to do that for you. It is not still there is no still artificial intelligence imbibed in such software, and so it is left to the engineer to identify the results given by the software. By the way, these different zones of the color or shades will be indicating different level of stresses. Various softwares that are available in the market, by and far ANSYS. ANSYS has the major market share as far as FEA softwares are concerned. But Abacus, Nissan, Astran, Pestran, Pro Mechanica, Katia. Lucy, hi Lucy, are you there?
Lucy's gone.
Oh,
With you're with me now with Kumo.
oh, I have just got a warning that the meeting would end after 5 minutes.
Oh no,
We,
please don't worry
we,
about that.
okay,
That's fine.
thank you so much. Thank you so much.
Okay, thank you.
Fine. So challenges pertaining to FEA, the challenges mainly are the output is only as good as the input, right? I normally say in my lecture that it's garbage in and garbage out. It highly depends upon the accuracy with the method in which you control the physics, the capacity of you approaching the problem largely will dictate the efficiency of the results of the process. While FEA is becoming more easier to use, a promise to democratize it eventually is still not into persistent, right? Because it has not become so intelligent that it will interpret results for you. And I normally say that FEA simulation is like a battlefield. It's like a battlefield. On a good day, you might not lose anything. But on some days, you may hit two mines with both of your feet. Right. Okay. So we will be having a separate stage where we'll be discussing about FEA and simulations, right? But let me move to the next phase, that is CAD data exchange formats. And this I am persisted to explain you about this because when we talk about two different softwares, let me say that I am having a Word document. I know that I cannot open a Word document into an Excel file, or I cannot open an XLSX file into a PowerPoint file. So similarly, a model created in Creo, CATIA cannot be opened directly into an analysis software. And so we do have something called as data exchange files or data exchange, which helps in interportability, or transferring models from one software to another. I have just given in this slide some standard extensions of various solid modeling softwares, like AutoCAD drawings will be DWG, Inventor would be IPT, Creo parts will be .prt, and etc. Now, if I'm supposed to use this same files and open it into ANSYS, I require some data exchange formats, right? Data exchange formats are basically standardized. And why do we have standardized? Because it is acceptable to any part of the country. It is even acceptable to different countries. So when I have got such data exchange format, I can always save that files into that format, which will be readily acceptable by the different software. These are various CAD exchange formats available in each and every modeling and analysis software. You can just go to, if you are using any software or if you use any software in future, you can just go and see file and save as. The save as options will have all of this. Say for example, if I'm working on SolidWorks, right? So if I want to import the SolidWorks model into ANSYS, I need to create it into any of this database exchange format. So these formats will be readily opened into ANSYS. Computer-aided manufacturing, again, use of computers in assisting manufacturing. In assisting manufacturing, when I say assisting manufacturing, it basically comes to precise manufacturing with high tolerance, with high accuracy required by aircraft parts, by automobile parts. They are normally manufactured with the help of computer assisted manufacturing tools. So CAM, when we talk about computer aided manufacturing or CAM, there are three basic technologies. One is known as the NC, which is basically known as only numerical control. CNC, which is supported by computer numerical control methods. And CNC is basically integration between CAD and CAM. When we talk about numerical control, there is no computer into picture. You should have your machining codes typed in a tape or in a pen drive, and you need to directly import it to the controller of that. And DNC is direct numerical control, where you will be having something like a master and a slave situation. One master computer will be governing multiple computers, multiple CNC machines. These are the brief comparisons of NC, CNC, and DNC, which you can obviously go through. right? And now I'm just talking about the working basic workflow of a CAM. Again, as I talked about, the prerequisite of CAM is CAD. Before you start with computer-aided manufacturing, you must have a computer-aided design model readily available with you, right? And when model is available, it is assumed that it has been analyzed and it has been optimized so that the product can be manufactured. The first step is CAD model import, where we'll be importing the CAD model designed in a modeling software into a manufacturing software, followed by process planning, wherein we do the tool selection, right? If your job or component is to be face machined or face milled first, and then you are supposed to have a slab milling, or you need to create some step, or you need to create some holes, then first you need to take an end mill cutter, then you need to take a drill tool of the required. So that is what we meant by process planning and selection of the tools. After that, the software will generate tool path for you, which will basically help us in simulations. That simulation will actually help us in identifying whether the tool is not fouling or it's not basically accidentally hindering to your manufacturing setup. Last, we will be having the machining, right? So I'll just have a brief demo of all of this in form of a video which I have already created in respect of time, because I knew that I won't be having much time to demonstrate it live. So this is step-by-step explanation of each of the step. Starting with the CAD, you are having CAD softwares like Autodesk Inventor, Dassault Systems, Fusion 360, etc. You need to create it to standard data, save it into standard data exchange format like STEP, IGS, and then import into softwares. Here you can see softwares like MasterCam. These are all manufacturing or CNC machining softwares. MasterCam, there is NXCam, there is Fusion NX. There are various softwares. Most popular, though, to me is MasterCam. Second is selection of tooling, depending upon the process plan that has been prepared for machining the entire component, followed by toolpath. The software will automatically create toolpath for you, wherein it will help us in setting up the cutting parameters, right? Setting parameters, like when we talk about machining, the parameters are widely cutting speed, cutting feed, and depth of cut. So it helps us in doing that. Followed by simulation. Simulation here will be showing you the toolpath, right? And various software shows different colors, or help takes help of different colors in order to show the toolpath. This toolpath will mainly be used to detect any collisions. Followed by post-processing. Post-processing here means creation of machine codes, right? By the way, CNC machines will work on specific programming codes known as M codes and G codes. Many of you might be aware of M code, which are known as miscellaneous codes, and G stands for proprietary codes. These are few examples of major widely used G codes and M codes, right? M are miscellaneous, which are used for preparations of the machine, like tool change, pull on, turn off, end of the program, while G codes are basically used to control the movement of the tool to machine the surface. Last, it has to take form of machining, where the codes, M codes and G codes, are directly transferred to the CNC machines, and then they are executed on a program. I am having a case study. I am having a case study wherein I will have a short video of around 8 to 10 minutes, which will entirely show how a model, the part which is being seen, shown on your screen, is like just a dumbbell shape, which is to be manufactured from a cylinder. I have taken very few operations, right? there would be facing operation, there would be turning operation, there would be taper turning operation. There are 3 or 4 different operations, right? But you can have a feel of it that if there is any complicated part, then also it can be easily done, right? Uh, I want your help in sharing the video that I have mailed you.
Okay, let me just check if I can share it from my side. Please hold on 2 seconds.
because because I was just trying it doing before the presentation, but I
Mm-hmm.
found that it was difficult for me to do that.
It wasn't working. Okay, let me just check on my side. 2 seconds. Please just be patient with me while I check.
Can I do it by directly sharing my screen?
Yeah, you can do that. You can definitely do that.
I
So what
tried.
you what you
Yes, yes, please help me out.
okay, can you see on the next to the leave button?
Share.
Yes, it's gonna say share content and then you'll select either the screen window or tab.
Okay. Should I share my entire screen?
Let me rather share it on my side.
Okay, that would be much more. I mean, that would be so nice of you to do that.
Okay, let me do that. Um, please hold on.
Yes, yes, there we go. I would be able to do that now. Hmm.
Can you see it?
Yes, yes, yes.
Okay, perfect.
Okay, okay. So before I start playing this, I have used a software called Creo, which was formerly known as PROE. It is a product of PTC, that is Parametric Technology Corporation, and the software is widely used in North American countries and in European countries. I have started with a already a solid model created, and I am then importing it into this software, and I'll just show you how these 6 different steps that I talked about. I just like to repeat that. First is CAD model generation that I have already done for you. I will be importing that model into this machining software. I will show you how process planning or tool selection is done, followed by toolpath generation. Then I will also show you the simulation wherein it will detect any collision if it is there, followed by post processing. So I start playing the video and the video is muted. I will just give some basic hints of what is being done. Uh, can you play it for me? Because the play button, yes, there we go. Okay. So, okay. So this is how I have started. I am bringing the already created model in the software. This turn 2 is the part which I have already designed. I have brought into the CNC or say CAM software. The part is now available. I am naming the part. That is, I am just creating a workpiece. I have also mentioned the tips for you. You can see the creating the workpiece. Why creating the workpiece? Because this was the original part that I want to be machined. So the workpiece needs to be of little larger dimensions. So I am just creating a workpiece I am creating a workpiece which is of little bit larger diameter, which has got some tolerance of 5 to 10 mm, both in the length as well as diameter. So you can see a light yellow workpiece created. Now it is green, and inside that is enclosed my part which I want to machine. Now what I am doing is basically creating the home 0 and the machine 0. I'm defining the home 0, right? People who are already into this profession, they are knowing, or who are operating CNC machines, home 0 is basically used to take the tool when the machining operation or a set of operations are completed. So normally it is 5 to 10 millimeters away from both the axes of the job. I am now just setting up. This is rough cut, so I'm just naming it as rough machining. This is phase number 2, that is process planning. I have selected the machine type. Normally, such cylindrical parts are machined on lathe machines. This is tooling setup, where I will use all the tools which are required, and I also need to specify the tool geometry like rake angles, clearance angles. This is selection of cutting parameters like feed, speed, and depth of cut. Right? You can see the depth of cut selected as 5 mm. So it will only cut 5 mm in one cut, move back, then again take a cut of 5 mm. I am defining the spindle speed as 1500 RPM. So that by I have selected the process plan, selected the process parameters, and now I go for creation of the tool path. Tool path generation. So you can see a single point tool coming into picture. I will just turn the view. This is an 3D view. I will just turn it to front view. I will change the orientation. See how the simulation works. It will show you. It will show you how exactly step by step 5 mm depth of cut will be taken, and it will be removing the material. The tool is retracting back to the home position. It's basically due to the, bandwidth issue, that it is moving a bit slower. The video is in bit faster mode. Every time it is retracting back to the home position, taking a 5 mm depth of cut, and then again machining it. So this is what a simulation or toolpath generation means. So that was the last cut. And now it is also going to do the facing operation. This is facing cycle, right? Because we also need to face the perpendicular surface to the axis. And it has to be only taken up to the center, right? Because the job would be rotating. Next would be finishing cycle. See, this is how the rough cut has taken the shape. Similarly, we need to again define a the finishing cycle, wherein the depth of cut would be different. This is finishing. Kumo, you can just move ahead a bit. You can just fast forward this because it is the same repetition. Again, the tool selection and everything.
Okay, no problem, no problem. Just let me know. Is that fine? Should I go forward?
Yes, yes, please. Yes, you can move ahead. You can move ahead.
Okay. Okay, should I close the video?
Yes, yes, yes. You can do that. You can do that.
Okay. Okay, I've closed the video. Should I then also should I bring back the slides now?
Yes, yes, yes.
Okay. Let me bring back the slides.
So this is what just I was showcasing how a digital prototype can be taken into realization, right? Though the toolpaths would now be converted into machine codes, and the machine codes are then fed to the machine. So the worker or the engineer working on the machine only needs to clamp and unclamp the workpiece.
I'm just waiting for it to upload. I'm not sure
Okay,
as to why
okay.
it's taking so long. That's that. Okay, there we go. Just just let me know when you can see it, okay?
Yes, yes. 2 or 3 more slides.
Okay, could you kindly take control from your side? But in
Yes,
the
yes, I have done
meantime,
that. I have done that.
oh, you've done that.
Yes, yes, yes.
Okay. Which page were you on? Do you remember which slide you were on?
Uh, I was on page number 54.
54. Can you see it?
No, it didn't move.
It didn't move.
No, no. Let me do it on my side. It won't take more than half a minute.
Okay, then please take control from your side.
Yes, 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 yes. I've done that. I've done that.
It doesn't seem like you have. To the attendees, could you just please let us know which slide you can see? Can you move it around? Can you go like one forward and one back?
I am on slide number 55 right now.
On my side, it's still showing slide 54. Just
It's now 56, 57. Is it moving? Yes,
okay, they can see 54.
yes,
Mm,
yes. I mean, it's moving now. Okay. So we are
I
coming to
think
the
it's
end.
I only think it's moving on your side and not. I don't think the attendees can see
Okay. I am
your
on slide
slides.
number 65. Can anybody let me know, audience? I am on slide number 65. Are you seeing that slide? Slide number 65. Only 54. How can that be?
So they can see mine. Can you please check on the
Okay, everybody is replying
above?
that it is 54. So I think I haven't got the control yet. I am just
Yes, you
taking
don't
the
have the
control. I am
control.
just taking the control.
Yes, now you've taken control. And
Yes,
now you're
yes,
on
yes,
65. There we go.
yes, yes. So these are
Can we just,
some.
sorry. Can we just get the attendees to confirm if they can see page
Okay,
65?
okay.
Future
Uh,
trends in CAD.
I am on. Yes, yes. I have got
Okay,
replied.
perfect.
I got replied that they are viewing my slide number 65. So I'm just talking about last, I mean, talking about the future trends that will be in computer aided design, because we all know that there is much more talk going about AI and artificial intelligence and whatnot. Couldn't bring them to screen. Try again. I am on slide number 65. Are you all viewing? Yes, Jason. Yes, Jason, you are right. I am on slide number 65. Yes, yes. So this will be the future trends, right? Where AR, VR will take control of all the training aspects. Virtually now, people have started implementing AR, VR, that is augmented reality and virtual reality. I visit to many industry where I see welder getting trained on this AR and VR. They do not have to physically go to the welding setup and try striking an arc or maintaining an arc. They normally do it in form of simulations and with the help of AR and VR. So this will be the future trends. Again, as we know, all of them here there is a type of mistake. It's future trends in CAM and not CAD, wherein you will be having IoT or remote controlled monitoring of the IoT control. I mean, sitting in my office, I will be governing some CNC machines but just by giving control with the help of an app developed on my mobile phone, right? So the days are not far away now. We'll be having again cloud-based CAM collaborative manufacturing. And last, you will also have something called digital twins, right? Digital twins is again a vast topic that would again take a lecture of for developing basic understanding. It will take a time of around 2 or 3 hours. But its digital twins is same like a twin, wherein you are having an actual manufacturing jargon or philosophy, which is basically which is basically controlled by which is basically controlled by a simulated setup on your laptop or your PC, right? So these are the few reference, right, which I have been using. With this, I come to the end of this presentation, and now I hand over to Kumu to briefly brief you about the upcoming programs.
Thank you so
Kumu.
much. That
Okay.
was a very informative presentation and also the visuals that you provided, the video. Thank you for that. I'm sure the attendees also appreciated that. And I'd like to thank the attendees as well for joining us. You know, you could have been anywhere else, but you guys chose to spend time with us. So we do appreciate your attendance. And I'd just like to let you know about our upcoming courses that ECT will be offering. So it's our higher education courses. It's two bachelors, one in industrial automation and the other in our electrical engineering, as well as for our masters, we've got two programs. So one is in power system analysis and renewable integration, and the other one would be in industrial automation and instrumentation control. So
I'm sorry.
it's okay, no worries. Thank you. So we are currently running a promotion for our professional certificates of competency. So normally they are £933. So if you do want to join us for our professional certificates, if you join before the 30th of November this year, you will then get a discount, and instead of paying £933, you'll be paying 599. So that's basically around £600 for our 3 month short courses. And then I've put in the chat, I've put in the promotion I'm talking about. So it's for any of our professional certificates. And then I'd also just like to let you know that today we do have a certificate of attendance, and there's a few things you need to note about that. So, one of the first things that you need to note about the certificate of attendance is that you need to fill out the form in 2 days from now. After that, it will expire. You will not be able to get it. Even if you guys would try and inquire, call in, it's going to be impossible for us to use that link again. So please fill it out within 2 days. And then there is a QR code as well that you can use. So you can capture that right now. You can use that. But if you want the link for the certificate of attendance, I am putting it in the chat now. So you can take a look at that. That's for the certificate of attendance. So with the certificate of attendance, you will receive it within 4 business days from today. If it's not in your emails, in your inbox, then it will be in the spam or junk mail. And then for the videos and for the video recording and the slides, that will be sent to you in 2 business days. And if you guys have any inquiries with anything to do with ECT, please reach out to this email that I've included in the chat. And then lastly, I'd like to just let you know that we do have many more events coming up for ECT, and you can just go ahead and use this link that I've provided, and then you can join us for our next webinars. Thank you all for attending, and I think, do you have time for questions? Do you want to take a few questions and then we
Yes.
can wrap it up?
Okay.
Okay,
Let me just we should visit the chat so that I can know. Okay.
sure, no problem.
Okay. And clear. Okay. How can we use CAD to design and model electrical systems? Right. So the topic was very generic today. It aimed at computer-aided designing and computer-aided manufacturing. And when it was with computer-aided manufacturing, I typically took a problem which pertained to mechanical engineering. That is a machining problem. But aided design has got no limitations. It is widely used by mechanical engineers, electrical engineers, civil engineers, architectural engineers, automation engineers. They are widely used systems. I'm knowing about few courses which are with ECT, that is basic engineering, drawing and CAD, wherein I teach that subject. So I know that there are various tools available in computer designing, wherein I teach students applications of CAD pertaining to electrical engineering. You can have entire. I talk about let me just because I was talking about two softwares, and my basic intention of talking about that two softwares is it is basically available free to you. So I was talking about AutoCAD and Inventor. AutoCAD has got entire library of each and every electrical components. So if you are supposed to design or prepare an electrical circuit, you can directly take the components from the library and just you need to collect harnessing or connect the wiring to the specific components. You will be having the electrical motor, ready library available where you can just pick and place each and every electrical component to design the circuit. You can just then have the connections. You can even simulate that. Hope I have cleared your doubt, Milya Minu.
Thank you for that. I'm
Okay,
sure
fine.
a
Nelson
person,
says, okay. Nelson says that
yeah,
I am interested for designing electrical system. I think I have answered that.
and
Uh,
then I think those are all the questions we have for today. Okay, I think there's one more that just came in. Oh no, they're just thanking you. And yes, once again, thank you all for attending. Thank you for joining us. And please be mindful of what I've said with regards to the slides and the recording of this webinar, as well as the certificate of attendance. So if we don't have any more questions, have a good day and thank you. Take care.
Thank you guys. You were an extremely wonderful audience. I hope you enjoyed it as much as I did in delivering the webinar. Thank you guys. Thank you so much.
Thank you.